So, now here is the talk about a framework for automated architecture-independent gadget search, brought to you by Tim Corner. Give a warm applause to Tim.
Okay. Can you all understand me? Is it like good for you? Okay, perfect. Yeah, a warm welcome. I hope you all survived the last 3 days of the Chaos Communication Congress so far. I heard about like this illness going around and making people stay in bed and stuff. So yeah, what I'm going to talk about today is a framework for automated architecture-independent gadget search. It's a research for my diploma thesis, and this specific topic here is work I did together with Thomas Dullian and Ralph Philipp Weinmann. So yeah, they had also their share of work. What we're going to talk today about is, first we're going to define the goal, what we actually wanted to achieve with this research. Then we're going to motivate why we did the complete research and what parts have been done before and why we were interested in looking in this will be discussed in the history section. And then we're going to go into the technical details in the strategy part and the algorithms part. And then I'm going to tell you what the current research state is and what further work can be done in this specific topic and the topics that are closely related to the return-oriented framework that we have written and the parts that it's based on. So we're going to start with defining the goal of the research, and that we want to use the term or the technique of return-oriented programming platform independently across multiple platforms without writing algorithms for all the platforms over and over and over and over again. So the independently and the multi-platform thing is like the main goal. Why? Most of the hardware that we see today that is used is x86 in desktops, is ARM for mobile handheld devices, but you also have a whole lot of hardware that is really interesting to play with and which is like really, really interesting to take a look at. Take for example like the cell architecture of a PlayStation, or you want to take a look at router hardware which might be based on PowerPC or MIPS, or you have Spark machines that you're interested in playing with. So you do not want to like redefine and reinvent the wheel for all of those architectures over and over again, and therefore we wanted to do something where you could write the algorithms once and then you could like reuse them on all the platforms. And what's one of those devices without the spirit? Because if you have cute spirits like those and you control them, it's kind of like a good motivation for me. Yeah, we have also a lot of things that right now already have a whole lot of computers in them. Like, for example, think about those automated vacuum cleaning machines that a lot of you people are buying and that drive around your rooms and stuff. You cannot like power them with an i7 core or something because it would like run out of power right after it left the charging station, right? So you need something different, and therefore we will see, like Ralph has put it pretty good in his talk, we will see like more and more devices in a lot more variety than we have today in a lot of the consumer devices that we use at home. Think about a refrigerator that like orders milk once it detects that the barcode scanner says all the milk that's already in the fridge will be like sour in the next day. Okay, we want to execute our code, like with return-oriented programming, we want to execute our code in the presence of non-executable memory. And this means for the architectures pretty much that they either have a software protection which does not let us execute any data of a program, but only the program code that was already there, or have defined an NX bit in the Intel case or XN bit in the ARM case or something like that. But we do not aim at any of the randomizations that you see currently. So given that you use return-oriented programming and or any other code reuse technology, then the main issue is always that you can only defeat one one specific part of defenses with it, and that is the memory protection that you have so that data cannot be executed. Given that you have any of the randomizations that are present in code, like for example in the new, in Windows or the PAX system or on some of the mobile phones that gets introduced now as well, you still need like a second bug where you kind of like get the information out of the complete program where all the data that you want to use in your code reuse attack is present. But as Sergey has put it in his talk already now, and I hope the next slide is not too convoluted or something, this is not really new stuff. It's like, I have done my share of work now, and I think that what I've done with Thomas and Ralph has not been done in this manner before because it has this architecture-independent thing to it. But generally, it's like there has been like a whole lot of work in this in the past, and it's one thing that I'm really eager to like get the point across, because a lot of people thought that return-oriented programming only popped up when Hawar Shaham released his 2007 paper on return-oriented programming for the x86, but there have been a whole lot of people that a lot of the earlier generations of hackers have learned a whole lot from, which actually have thought about all this stuff a lot earlier than it the academic world might reflect now. So if you just take a look at the colors of this slide and you see how predominant the red things are in the early history of any code reuse attacks, then you see that the history of technology is not always based on the academic world, or might not just be recognized by the academic world. In the first paper that Hawar Shaham actually released, there was not that much citations of like the normal history book of hackers like Bugtrack or Frack or any of the magazines that have been out there. And it's like really important for you to understand. It's like the history of stuff and the history of the complete hacker community, it's out there. And it's like you can read stuff that hasn't been published in academic papers and hasn't like gotten anywhere. So there is one really interesting example actually, and it is like he told me he didn't realize anymore when he actually posted this small example, but this here is pretty much one of the things that Gera in this case put up in his series where you could like learn exploiting, and alone the question that he asked you is pretty much the same what return-oriented programming now aims at. And it's basically, your mission is to behave the program like this other program, but you cannot execute code in a stack. And that's the thing which we aim at with return-oriented programming all the time. So, after I've told you what I think is the history about that, I might be wrong because I haven't had a chance to like get all the information together, but Sergey did also a pretty good job. I think our history only differs in like one specific point in time, which is related to a Bugtrack discussion in 2000. We're going to switch now to the strategy that we are using for our architecture-independent gadget search. Basically, return-oriented programming always only uses present code, which is either present in the executable itself or in the libraries that it uses. What we do not do is something that recent publications have sometimes kind of like a little bit misunderstood. That is, that we do not use a single instruction return-like approach. So what other return-oriented programming people have done is that given that you have a variable length instruction set, like the Intel instruction set, you can easily search through the executable on a hexadecimal display kind of level and just search for opcodes like the return opcode and then one instruction before that to form your gadgets, because it's really simple, because you can use unintended instruction sequences. Due to the fact that we want to be able to be architecture independent with our research, we cannot use only unintended instruction sequences, because a lot of the architectures that we want to aim at also are not variable length instruction sets. Like ARM, for example, has 32 or 16-bit, and PowerPC has 32 or 40 or 64-bit. So we are actually using more information in front of the return or the, as we call it, free branch instructions. We actually use RILE, which is the reverse engineering intermediate language that we have developed at Cynamics, and it makes it able for us to have an intermediate representation of all the assembly languages that we have been able to transform into RILE. And due to the fact that we use RILE, we can write our algorithms so that they utilize the RILE language and not the native assembly language, which makes it very easy for us to be architecture independent once one of the native assembly languages has been translated into RILE. But I'm gonna have a short next slide where I'm gonna go a little bit more into detail about the RILE language. As I have already told you, what we return-oriented programming kind of is phrased after that you use return instructions to chain your instruction sequences together. What we did is that we defined a free branch instruction rather than only returns, because in multiple architectures it's not only possible to use return instructions but also jumps to registers or in ARM, it's even possible to use any arithmetic instruction to actually change the program counter. So it is not that really a good thing to only take a look at return instructions, because your possibilities are a lot wider than that in most of the architectures. So also, even though there have been recent advances in actually, I don't know if you heard about Pablo Solis' work that he did with Sean Healy together in the immunity debugger, where they use a SMT solver to actually only find the gadgets that you need. What we do is, due to the fact that we work on this completely static, is that we have a first find all, then filter useful ones approach, which means that we try to find all or locate all the instruction sequences which might be useful for gadgets, and then filter the ones out that we can actually use. And we try to keep an eye on side effects, but more on that later. So what's RILE all about? RILE is a very small RISC instruction set. It's comprised of 17 instructions for arithmetic, control flow, and MISC functionality, and the instructions are always side effect free. If you compare that to any of the assembly languages that you might know, like for example in addition in x86 or something, then there is only it's like everything is like implicit. All the flags are implicit and stuff like that. It's stuff that you don't really see. But it's not like if you don't know the assembly language, you can easily get lost in it. In RILE, everything is explicit, so each instruction only has the effects that you can see in a single instruction. Therefore, single instructions get translated into multiple RILE instructions all the time. We have an interpreter for RILE, which has virtually unlimited memory and temporary registers, and is implemented as a register machine to reflect the architectures that we want to take a look at better than as if we would have a stack machine. What we do not have support for is exceptions, floating point instructions, and 64-bit instructions yet. But this does not really matter to us, as exceptions mean in this manner that if you take the MIPS instruction, the MIPS assembly language, for example, you can have for each signed addition or something an exception that is actually encoded in the assembly language. And it is very, very hard for any translation, because you do not have any program state to know if this instruction occurred or not, because you're not working on you're not working on the data, but you use a static translation, like a mapping. Okay. After we have now learned what we want to achieve, we're going to dive into the algorithms that we use to extract the information out of the binary, which we can later then use to define our complete gadget set. In the first stage, what we're going to do is that we collect all the necessary information from the binary that we need to later be able to get an idea of the semantic information of certain paths and their instructions on and the instructions on those paths. Then we're going to merge the collected data of instructions and paths together, and later we try to have a fuzzy tree matching which matches fuzzy defined semantic information with the information that we have extracted from the binary, so that we can see if the sequence of instructions that we could currently take a look at matches something that we can need in our programming later. In the first stage, what we do is that we extract expression trees for native instructions. Native instructions means, for example, an addition or something in the x86, ARM, MIPS, whatever assembly language. And it's like a basic expression tree looks like this. It's just like if you have like an addition of a register plus an integer value here, then you just have that all the leaves of the tree are actually operands, and all non-leaves are operators. So that you can have a representation of the arithmetic that the instruction has in like a tree form like that. We need that later on because it enables us to combine the information of multiple instructions in sequence still in a single tree so that we can make assumptions over what's going on. What we also do is that we extract path information. We do this from like the bottom up, so that we basically start at any of the 3 branch instructions that we earlier defined and walk upwards until we find an instruction that we cannot handle, like a call where we cannot know what kind of semantics are behind the instructions that the call would do, or behind any instruction which we cannot handle, like an exception or a floating point instruction or something like that. So to extract the expression trees, we have handlers for all of the possible while instructions. And for most of the while instructions, those are very, very simple handlers. Like, for example, you have an addition in while, which only has like 2 operands which it takes as input and 1 operand where it writes the result to. Then we save the information of the expression tree under the flag of the result and save the expression tree. Very, very simple. For all of the arithmetic functions, this is like something everybody of you can understand quickly. But we have one problem or 2 problems, and that is due to the fact that we need to save all informations over a certain path. We need to make sure that each memory location that gets written and might be addressed by a register will not get overwritten in the instructions that follow it by again using the register for something different. So it's very, very necessary here to uniquely identify all of the memory areas that you write to, because otherwise information would get lost. What we also need to take into consideration is, given how many of you know ARM, like as the assembly language of ARM? Okay, so you might be aware of that there's like, for all of the 32-bit instructions in the standard ARM instruction set, it's possible that you can have conditions, and it's like 16 of them, to decide whether the thing is going to be executed or not. And like, therefore, in a single native instruction, it's totally feasible, and you have other instruction set where this is also possible, that you can have conditional execution within one instruction, right? One native instruction gets translated into multiple while instructions, and now that you have a condition in there, because it's only executed if a certain set of flags is set, then it's problematic for you, because later on you want to have those trees of this specific native instruction encoded such as you can always, only depending on the flag, decide which path of a tree is going to be taken, and therefore you have to take special care if there's conditional execution in there. We do this by actually encoding both sides of a conditional execution in one single tree, and make sure that we can have both of the sides in the expression tree, so that we do not have to split the instruction. Okay. Yeah, path is extracted in reverse control flow order. I've already told you this. We start at the 3 branch instruction and go upwards from there until we meet something that we cannot handle. So what did we learn now? What we learned is that we can extract for a native instruction expression trees, and we can extract paths from the executable until we don't know how to go further, or if we reached a threshold which we do not go any deeper into. And what we use this now for is the stage 2 algorithms, where we actually take this data about single native instructions and merge them along a path so that we can have all the information of all the semantic information of all native instructions which are executed along a single path, and have a complete semantic information about the instruction sequence later on. Also, what we need to do, as we extracted the paths in reverse control flow order, it might totally be possible that we cross a jump which is actually conditional between basic blocks. And therefore we need to make sure that we encode this information into a special register, into a special expression tree, which we also include in the complete expression trees for this instruction stream. And also what we need to do, as RILE is pretty, it's pretty loud in translation, so we need to simplify the result, because given that you have an instruction that has multiple additions or multiple subtractions from a single register, you do not want to really keep that all, you do not really want to like have all those operands and all those leaves in a single expression tree, because it doesn't make no sense. Okay, so combining expression trees along a single, along a path is pretty simple. You can take this very simple arbitrary example here, and given that you have a set of expression trees which comes out of a sequence like this here, then later on, due to the fact if they reference on the same register, like here or here, you can combine them to larger trees. And therefore, you limit the information that you get out of it. And what you gain from that is that after this sequence of its instructions, you have a marker for R0, and it's only a single expression tree that explicitly defines what behavior is going to be done on R0 after execution of these instructions. If we now have a branch instruction in here somewhere, and we know, because we have the expression tree of this branch instruction also, that in this specific case, a specific flag must be a specific condition, then we can generate a condition tree and also put that into the complete forest of our expression trees for this instruction stream. And simplifying the result, as I told you, RILE is pretty loud in translation, and due to the fact that we know a little bit about the architecture, or know a little bit about what type of RILE translations we do, we can actually simplify the result, because all the additions can easily be put together, and an R0 doesn't have any effect, and an AND with all Fs is on a 32-bit architecture, no effect as well. So after we have now merged all the native instructions along a path and put them together so that we have the semantic information extracted for all the instructions that are executed along a single path, we need now some kind of way to define what we are actually looking for. Because given that you want to have, as the return-oriented programming thing suggests, a Turing-complete gadget set for a specific architecture, or in our case for any architecture that we have translated into RILE, we want to be able to locate useful semantic information that we predefined. So this is what we're actually going to do in stage 3. So searching for useful gadgets in the merged data is nothing else than use tree match handlers and compare those fuzzy tree match handlers to the trees that we have already extracted. So given that we know how we want to have a specific addition look like, or we want to have a register addition look like, or a memory dereference look like, we can just use a simple tree match handler, which is kind of fuzzy, so that we find more possible references, because we do not really care about if explicitly the memory address of R0 is addressed, but we can also use R0 plus 4 or N. we can use that with this tree match handler. And what we want to do is, given that we have more gadgets which we can take a look at, is that we only want to take a look at the simplest gadget which performs a specific operation, because we want to minimize on side effects, and the larger the trees and the more trees we have, the more side effects we're going to have. So how does this work? It's, as I told you, pretty simple. It's basically, you have a tree like this, where like the leaves here might be even with addition or subtraction or even multiplication, and we match that to all the gadgets that we have found in the executable. And for the second case, given that we have a whole lot of trees found which perform the same thing, so where the tree match handler already matched something, then we only want to select the most simple gadget here, because given that we only have this very, very simple gadget which we actually can use, then why have effects on a lot more than we actually need? Complexity reduction is one of the key aspects that you always have to take into consideration, because complexity kills all the good stuff. So, what are the results of the whole thing? Algorithms for platform-independent, return-oriented programming are totally possible. For ARM, we have shown that we can even use those gadgets that we extracted here from binaries and have a compiler that compiles them for iPhone payloads. We are able to find all the necessary gadgets for return-oriented programming with our tools, so that it fulfills the Turing completeness thing that return-oriented programming has. It always depends a lot on how large your binary is, though. If you have like returnless kernels or something like that, as I have heard some people have done now, it might be a little more difficult, but there's always a way around that. Searching for gadgets not only very platform, but also very compiler dependent. In the initial tests that we did with that, like in the mid this year and last year, was that given you compare the same source code output from a Visual C compiler, a GCC, and maybe like a Borland compiler or something, they emit totally different code. And depending on the optimization level, they emit totally different code. So the gadgets that you find in specific things is always completely different. So that was one of the reasons why we actually tried to make the tree match handlers that we used for gadget recognition kind of fuzzy, so that we would find stuff which is semantically a little bit equivalent. It's a hard word, like to use semantically equivalent here, but it's just to like get the point across. Yeah, minimizing side effects is also possible. If the approach is chosen that I have shown you, there's like some explicit things that you can also do, but it makes it a lot simpler for later on SMT solver stage to actually use the gadgets in a programming kind of way. Okay, what is the further work that we have to do? An abstract gadget description language and the automatic gadget compiler for all platforms is one of the things that is really, really not that easy. I've seen the work that Sean Healy and Pablo Sole did now for the immunity debugger. I really admire the work a lot, but I think that it's like for our approach that we have here, we need something that that's even a little more abstract than what they are using, but we haven't gotten around to like define this more than for the ARM case where we have shown it to work. Yeah, automatic gadget compiler for all platforms, so that it's possible to not only use it on ARM and to like have it work on the whole thing. Bring more platforms to Rails, so if any of you are interested in porting your favorite embedded processor to an intermediate language to use all those algorithms on it, you're very happy to talk to me. I'm very happy to talk to you and better understand the implications of different compilers. As I already told you, it's one of the major things that you always have to keep in mind. So thank you very much for listening. I hope you enjoyed the talk, and if there are any questions, you can come to me.
did you port Intel?
No.
Okay, thanks.
Yeah, it's ported to RILE.
Yeah, that was my question.
Okay, yeah, it's ported to RILE.
Okay,
you can, if you want to work on x64 though, awesome.
Nice.
I got a question. How do you go from opcodes to disassembly and to RILE? Do you have to manually?
Okay, yeah, the complete translation process. Actually, I enjoyed your talk a lot. First thing. What we do is we have the complete thing is coded in BinNavi. It's like the tool that we have written at Cynamics, and what we use as disassembler currently is IDA Pro. And what we have for IDA Pro is we use an exporter which takes all the information that we get from the disassembly from IDA Pro and put that into the database. And from that database, we have the RILE translation, which is done on the fly once it's loaded into BinNavi. We have binary, IDA, BinNavi, and RILE, and then the algorithms on top of that.
But do you automatically generate the transformations for each instruction, or do you have to manually make the mapping from
everything's automated.
Okay. Thanks.
Hi. Do you have any suggestions for, well, let's say, how to make current computer systems more secure against this approach? Because, yeah, well, we can break stuff now, but which is fun.
Like, as I have already said, it's like which return-oriented programming and like all of the code reuse attacks I know of are quite vulnerable to is like randomization in general. So if the operating system vendor or you specifically for your program like remap the program on every start, then it's pretty hard because return-oriented programming relies on static addresses for all the gadgets to actually like execute any of the code. But the thing is, given that today is already like the trend is going on that you use multiple bugs to exploit vulnerabilities. So that you have the first stage is kind of like an information leak where you get the addresses from the program you're exploiting in some way, and then later you use something like any of the code reuse techniques that are out there and like use the information you extracted and then circumvent any of the data execution prevention kind of types. So there have been people that promote stuff like program shepherding or shadow stacks and stuff like that, or like make sure that in front of a return is only a certain type of instruction and that the shadow stack is actually the same like the normal stack and stuff like that. But as the program shepherding idea, as far as I remember, has been put into a tool by Determina, and they haven't been very successful with it in the past, I doubt that this is a really, really feasible idea. So I think that if you have smart randomization, and you do that like on every program start, and load libraries always differently and stuff like that, you're pretty much well protected given you don't have 2 bugs in your program. But yeah. I hope that answers your question like a little bit. Okay.
Okay, now we come to the last question since we are very tight on time. And afterwards you can go directly to Tim if you have something other to ask.
Yeah, I also got like cards with me if you want to write me an email or something, so you don't lose it. It's on paper and stuff.
Hello.
Hi.
Certain architectures actually execute instructions non-sequentially. Example, given the MIPS architecture, where you have branch delay slots after each jump or branch instruction. How do you propose to handle such architectures? Because you really have to predict the branch or to know that this particular jump is going to happen.
Yeah, right. That's like one of the cool things if you take pass from like the bottom where you actually come from, like where you actually otherwise would go to, because you know the branch before that. If you have any conditional branch and you're actually going the false side, then you know the branch delay slot won't be executed, and given the branch is taken, it will be executed. The thing that we really thought long about, I think it was like in one of the earlier MIPS description things, was that you could have a likelihood of the branch, right? I remember like the plus or minus thing. And then there was like this one special condition where actually the branch delay slot did like something totally different as in the new specifications. I don't remember exactly how it was, but there was like something that we thought about long. And it was really a pain in the ass to translate it into RILE to get it like, because you have to execute it before the branch. And it's like really hard to do that if you have a one-to-one mapping in a translation language, but we found a way. If you're interested in the details, I can show you stuff where how we do that, and maybe you have a better solution about that, because it's like with Spark, you're going to have the same problem, right?
Yeah, Spark is quite similar
it's like
to MIPS.
if you, coming back to the original question, if you start from the bottom of an instruction sequence and you go upwards, then you kind of know which side of the branch is going to be taken. That's kind of like the solution right here. Is that answering your question? Okay. You're deaf.
So, thank you, Tim.